Hi, everyone. So one important thing to remember about vector spaces is that because the definition is axiomatic, anything that satisfies the axioms counts as a vector space. And the operations that we call addition and scalar multiplication don't even have to look like the things that we normally recognize as addition and scalar multiplication. So addition and scalar multiplication can be anything as long as the axioms hold. So if you have some kind of weird addition and scalar multiplication rules, it's useful to use different symbols for them, just so you don't get confused with ordinary addition and multiplication. So when we're working with weird addition and scalar multiplication rules, we're going to use a plus sign with a circle for the addition and a star for the scalar multiplication. So here's an example of this kind of weird vector space. Let V be R plus, the set of positive real numbers. And then in place of addition, we're actually going to do multiplication. And so what I mean by that is that in this vector space, the vector space operation of addition is actually multiplication. I know this will take a little getting used to, but hopefully you'll get the hang of it after a little while. And then the rule for scalar multiplication is actually exponentiation. So k star a is, by definition, a to the power of k. Now, it's worth remembering that in this context, k can actually be any real number, positive or negative or zero. In this case, the vectors are positive real numbers, but the scalars are real numbers, and that's always the case. Whenever we're talking about vector spaces, the scalars are real numbers. So anyway, why are we allowed to define addition as multiplication and scalar multiplication as exponentiation? We're allowed to do that because they satisfy the axioms. So I'm going to go through the process of checking some of the axioms for you so you can see how that works. But first, let me just try to convince you that this does work just by demonstrating that the algebra works out correctly. So for example, let's say I have an expression like 2 times 3 plus 4 with the weird operations. The rules of algebra say that I should be able to distribute the multiplication over addition. And so, if the algebra works, it should be true that 2 times 3 plus 4 should be equal to 2 times 3 plus 2 times 4. So is this true in this case? What we're going to do is we're going to rewrite both sides of the equation in terms of ordinary arithmetic. So remember, the plus with the circle actually represents multiplication, and the star actually represents exponentiation. And so that means that the left side of the equation is 3 times 4 to the power of 2. And then the right side of the equation is actually 3 to the power of 2 times 4 to the power of 2. And now you can look at both sides of the equation and you can say, yeah, it does work. Those two things are equal. And the point is that after we check that the axioms are satisfied, then this sort of thing will always work. Okay, so we want to check the axioms in this example. And before we do that, it'll be helpful to quickly review the axioms and rewrite them using these symbols that we've been using for the weird vector space operations. So the first axiom is associativity, and we're just replacing the plus sign with this plus with a circle sign. And the second axiom is commutativity. Okay, at this point, there's nothing too weird. But now, the third axiom is interesting. This is the axiom that says that there exists a zero, but 0 doesn't have to be the thing that we normally think of as 0. 0 is defined by this axiom that says that when you add 0 to anything else, you get the same thing back. In our example, our vector space just has positive real numbers. It doesn't actually have the number 0. But that's not the question to ask. The question is, does there exist something such that when you add it to other numbers using the weird addition operation, you get the same thing back? So to avoid confusion, I'm going to use a capital Z to represent this 0. And this 0 is defined by the property that A plus Z is equal to A for all A in the vector space. And then there's a similar situation with axiom 4. This is the axiom that says that there exist minuses. But again, the minuses don't have to be the thing that we normally think of as minuses. They're just the things that when you add something to its minus, you get 0. So this axiom says that for every A in the vector space, there should exist some quote-unquote minus a, such that when you add a plus minus a using the weird addition, you get z. All right, and then axiom 5 is one of the distributivity laws. It says that when you have k times a plus b, that scalar multiplication distributes. This is actually the axiom that we saw in practice on the previous slide. Axiom 6 is the other distributivity law, which says that k plus l, scalar multiplied by a, will distribute. And you'll notice that there is something interesting here. That plus sign on the left, that actually is the usual addition of real numbers, because k and l are scalars. The scalars are always real numbers, and the operations between scalars are always the regular operations of real numbers. And so then axiom 7 is the scalar associativity axiom, and something similar happens there. On the left-hand side of the equation, you're multiplying the two scalars, k and l, and so that's the usual multiplication of real numbers. Whereas on the right, you're scalar multiplying by L and then scalar multiplying by K. And so you're using the rule for scalar multiplication in both cases there. And then axiom 8, the 1 axiom, just says that 1 scalar multiplied with A is equal to A. And again, this is the scalar 1, and so there's nothing weird about it. It's the usual number 1. So the key thing to remember throughout all this is that when we have weird vector spaces, the vector space and its operations can be weird, but the scalars are always just the real numbers with their usual operations. Now, some of you might ask, why can't we have weird scalars? And the answer is, well, you can, just not in this class. That's something that you would learn about in the modern algebra class, so take it. Okay, so anyway, we want to check that the weird example that I gave you earlier, where addition is actually multiplication and scalar multiplication is actually exponentiation, we want to check that that satisfies the axioms. And of course, it would take a long time to go through all 8 axioms, but I'll do a few of them just so you can see how it works. So just to remind you, we're talking about the situation where the vectors are positive real numbers and where this plus sign with a circle actually represents multiplication, and where the star symbol actually represents exponentiation. So let's start with axiom 1. One way to check this is to write out the axiom, but put a question mark there because we don't know yet that that's true. That's actually what we want to check. And so to check that it's true, we're going to work on both sides of the equation and replace the weird vector space symbols with the actual operations that they represent. And you might be able to do it all in one step, but I'm going to do it step by step, working inside the parentheses first. And what you end up with is a times b times c versus a times b times c. So now we've expressed the equation in terms of ordinary arithmetic, and we know that this is true. And so that's it. That's how you verify axiom 1. So now let's look at axiom 3. This one is a little bit different from 1 because there isn't an equation to check. We actually need to find what the z is in order to verify this axiom. So to do that, we'll write out this equation, a plus z is equal to a, and sort of like what we did in 1, we'll rewrite it in terms of ordinary arithmetic. And because in this case the weird addition is just multiplication, we get that a times z is equal to a. So now what we want to do is solve for z, and of course we get that z is equal to 1. So this is interesting. In this weird vector space, the 0 is actually 1. All right, I'll do one more of these and leave the rest as exercises for you. Let's look at axiom 6. This is similar to axiom 1 in the sense that you can verify it by putting a question mark on top of the equation, unraveling both sides of the equation, and then eventually getting to a place where you can see that they are equal. And when we unravel the left-hand side, we get a to the k plus l. On the right-hand side, we can first work inside the parentheses to get a to the k plus a to the l, and then we can unravel further to get a to the k times a to the l. And now we can look at that equation and say, oh, that's an equation that's true. That's one of the exponential rules. And so that verifies axiom 6. And you'll notice if you go through the other axioms that something similar to what just happened will continue to happen. You'll see these rules that you learned about exponents appearing in the verification of these axioms. So another question you might ask is, why does this happen? Where does this weird vector space structure come from? Well, there's actually a pretty nice explanation for it. So suppose you have two people that are communicating with each other across some distance, Ray and Kylo, and their communications are a little bit weird. They're on different sides of the Force, and so there's some transformation that happens in the process of their communication. If Ray thinks of the number 2, then the number that Kylo hears is 4. And if Ray thinks of the number 3, then the number Kylo hears is 8. So the general rule is that the number that Kylo receives is 2 to the power of the number that Ray is thinking of. So then what happens when Ray thinks of an expression like 2 plus 3 equals 5? Well, then the expression that Kylo receives is 4 plus 8 equals 32. But Kylo knows that the addition might be weird, and so he uses the symbol for weird addition. And indeed, Kylo realizes that this weird addition is actually just multiplication. So what's kind of neat here is that we're seeing that it's not just the numbers that are changing as you go from Ray's perspective to Kylo's perspective. The operations, like addition and multiplication, are also changing. And when you do that, the properties of those operations, like distributivity, associativity, and so on, those properties will hold equally well from Kylo's perspective as they did from Ray's perspective. And actually, we'll see later that this sort of explanatory process where we can explain weird vector space operations as just some kind of translation of regular operations, we'll see that there's always some way to do that. But that's something that we'll get to later.